And hello everyone, Paul here to talk a bit about minerals and rocks today. So first of all, what is a mineral? Well, to a geologist, a mineral has um, a very specific five-part definition. First of all, they are naturally occurring, nothing weird that you cooked up in a lab, no plastics or anything strange like that. They are inorganic, so not alive or generally part of living tissue, although bone and teeth are kind of an exception to that. Um, they are solid, as opposed to liquid or gas. They have a very definite chemical composition. Minerals have chemical formulas. SiO2, NaCl, etc., etc. They have chemical formulas. So in this sense, a chemist would call them like a chemical substance or something like that. The other thing they have is a crystal structure. Now, we don't mean they're always great big honking crystals. What we mean is that internally the atoms are arranged in a very regular way. This is the mineral quartz, for example, that is nothing but silicon and oxygen. And so we can see how they're stacked in a very regular way. That's what we mean by crystal structure. Okay, alrighty. So if that's a mineral, and we'll talk separately in the lab about identifying minerals. Here we just want to worry about a definition. If that's a mineral, then what's a rock? Right, as we look at this really picture of what we call columnar jointing of some rock, I believe in Iceland. So what is a rock then? Well, a rock is a couple things, or one or two things. Most rocks are just combinations of minerals. So, for example, that piece of granite that you see there, it's got some quartz, it's got some feldspar, it's got some amphibole or something like that in it, and it's a combination of minerals. Most rocks are like that. Most rocks are one way or another a combination of minerals. But there's also rocks, in particular what we call chemical sedimentary rocks. Um, that are almost minerals. They have all the criteria except a crystal structure, right? This is a piece of limestone on the right. Limestone is, naturally occurring. It's inorganic. It's solid. It actually has a chemical formula, CaCO3, right? That granite doesn't have a chemical formula. I can't rattle off a chemical formula for granite because it would depend on where you sampled it, right? The chemical formula here is different from the chemical formula there is different from the chemical formula, there. So yeah, this though is CaCO3, which means that it's almost a mineral, except it doesn't have a crystal structure. And if you don't have a crystal structure, you can't be a mineral. This is just mush, calcium, carbon, and oxygen, and is therefore not a mineral. Most rocks, though, are combinations of minerals. But every now and then we get, like I said, chemical sedimentary rocks that would be a mineral if not for the lack of a crystal structure. So as we think about rocks, there's three kinds, as we know: igneous, sedimentary, and metamorphic. Igneous rocks form from molten rock, magma if it's below ground, lava if it's above ground. We'll talk about them more. We'll talk about each of these more. Sedimentary rocks form either from sediment, so like sand getting turned into sandstone or something like that. Or, like we just said, from chemical precipitation, right? This limestone back here formed when calcium, carbon, and oxygen in the water solidified out of the water to make this rock, right? We call that precipitation. And you can have a whole variety of rocks form that way. And then we also have metamorphic rocks that form from other rock, from applying heat and pressure to other rock to make metamorphic rocks. We'll talk more about each of these. Let's begin with igneous, though. So igneous rock classification is based on two things: composition, which is what is the rock made of, and texture, which is how big are the mineral grains. No matter how far you go, that's what igneous rock composition is based on. We can see here two differences in composition. This rock is very dark in color. This rock is very light in color. That's composition. Texture. Here you can't see any mineral grains. Here you can. Texture. Okay, so let's talk about composition though a little bit more. The thing that we track for composition is silica, SiO2, silica. Silicon and oxygen are the two most common elements in the Earth's crust, and so they're everywhere, and so that's what we keep an eye on. Um, for igneous rocks, there's three basic compositions, mafic, intermediate, and felsic, and these depend on how much silica the rock has. Mafic rocks don't have a whole lot of silica, and they tend to be darker in color, like this rock on the left here. Felsic rocks, all the way on the right, tend to be lighter in color and have a lot of silica in them. Okay, and then in the middle is intermediate, which usually make by literally mixing these two rocks, which we'll talk about. But so intermediate, so not a whole lot of silica. In absolute terms, by the way, it's still about 60% silica, but relatively speaking, not a lot of silica. More silica, a whole bunch of silica. Not a lot we call mafic, a little more we call intermediate, a little more we call felsic, right? Here's what a mafic igneous rock looks like. This is basalt, right? Hawaii is basalt. The entire seafloor is basalt. Usually when you see lava flows, they are basalt. This is the Deccan Traps in India. A whole bunch of lava flows stacked one on top of each other. Here's the Valley of Fire in Texas with a nice pretty lava flow. Here's the Giant's Causeway in Ireland. A lava flow that when it cooled, popped into these columns. If you look at it from the side, it looks like that, called columnar joints or columnar jointing. This is a fairly common thing. Once you know to look for it, you're going to see it everywhere. People think it's made by people. It's not. It's a totally natural thing. Under the right circumstances, when these lava flows cool, they contract into these hexagonal columns. It's called columnar jointing. And once you know to look for it, you're going to see it in a lot of places. Here it is in Oregon. You can see a nice lava flow there with columnar jointing in it. Intermediate composition rocks kind of look like that. They're kind of evenly dark and light in color. And the big thing here is like the volcanoes of our Cascade Range. Mount St. Helens, for example, which is what you're looking at here, are intermediate in composition. These are made when you combine that mafic seafloor with that felsic crust at ocean continent convergent plate boundaries. And we'll talk more about that when we talk about volcanoes. Felsic rocks, very common. Granite is one that you hear about a lot. Mount St. Helens, not Mount St. Helens. Stone Mountain in near Atlanta, Georgia, is a big old honking piece of granite. There it is from the side or from the back, the quote unquote back of it. You can't really walk up the front, but you can hike up the back. So if you're ever in the Atlanta area and you're looking to kill some time, Stone Mountain is really just beautiful, beautiful place to visit. Yosemite out in California also. Everything you see here is granite. All of this is granite. Big, huge body of granite. Granite comes in colors, right? Where, white and pink, right? It has to do with the feldspar of the rock. This mineral right here this pinkish mineral can be pink or it can be white. White feldspar makes white granite. Pink feldspar makes pink granite. Here's the Llano granite out in Texas, out of which the Texas state capitol is made. Granite is very commonly a building stone. There are government buildings here in Pinellas County that are made out of the Stone Mountain granite. By the way, the quarry out there had a contract with the federal government for a long time to provide building stone. So that's composition. Mafic, intermediate, felsic, not a lot of silica, more silica, lots of silica. What about texture? Well, texture just refers to how big the mineral grains are, right? And this is related to the cooling speed of the rock. And the cooling speed of the rock is related to where it cools. Rocks that cool underground tend to cool slowly and tend to have make these rocks with large visible crystals, right? And so like this rock here, this granite here. So we call that coarse grained, all right? So coarse grained igneous rocks cools slowly, and that slow cooling happens below ground. Okay, up here we have a fine-grained igneous rock. It cools quickly, and that quick cooling happens above ground. And so these two rocks are kind of interchangeable in that they have the same chemistry. If I was to melt down this granite and cool it quickly, it'll make that rhyolite. If I melt down this rhyolite and cool it slowly, it makes that granite, right? And so without knowing anything else, if you just pick up a rock, you can tell how fast it cooled. If you can see mineral grains, it cooled slowly, and we call that coarse grained. If you can't see mineral grains, now once again, squinting and maybe see, no, the rock is not made out of visible interlocking mineral grains. We call that fine grained, and it cooled quickly. Right, here's Stone Mountain again. It's granite. It cooled slowly, right? That happens underground, and yet clearly it's not underground, right? So what the heck? Well, what the heck is, this rock is about 300 million years old. This rock formed when Pangea came together, when South America, North America, Africa, and Europe all smacked into each other, and deep down, it got hot enough to melt some rock and turn it into magma. And then after cooling a bit, turning to magma, then it worked its way upward a bit, and then it cooled underground, completely underground, making a coarse-grained rock. Then erosion, right? Erosion moved the ground surface down to the rock, right? I mean, once the rock cools, you can't move it up anymore. You just can't. And so if you can't bring the rock to the surface, bring the surface to the rock. And that's what happened here at Stone Mountain. And this is why, this is the kind of thing that geologists do. We're not interested in just, oh, look, it's a granite. We're interested in the story that tells. Here's like these pairs of rocks, right? Here's granite and rhyolite. The only difference is the texture, right? Coarse grained, cooled underground, fine grained, cooled above ground, right? Here's gabbro and basalt, same thing. Coarse grained, cooled below ground, fine grained, cooled above ground. And in fact, if we combine those three different compositions with those two different textures, we get the 6 rocks. We get gabbro and basalt, diorite and andesite, granite and rhyolite, depending on where they cooled, below ground or above ground, and how much silica they have, right? Both of these have a lot of silica. Both of these have very little silica. Both of these are somewhere in between. And the grid that you use to identify igneous rocks looks something like this, only without the pictures on the grid. A couple other things, though. Pumice and scoria. Both of these are vesicular igneous rocks in that they have air bubbles in them. Pumice is felsic and scoria is mafic. Pumice is a very light rock, has very low density, so low in fact that it will float on water. I don't know any other rock that floats. Scoria is not that light in weight or density, but it does have these large visible air bubbles where gas has escaped from it. When you go to the store to buy lava rock, you're buying scoria, either for your grill or landscaping or something like that. You're buying scoria. And then, both these have air bubbles. The pumice does too. They're just very, very small. And scoria, they're big enough to see. Many of you have heard of obsidian or volcanic glass. This is what happens when the rock cools very quickly, right? Like in minutes, right? Making this rock requires that the lava flow into the ocean or into a snowbank or something like that, right? It's not just going to cool, it's going to be quenched. Obsidian is almost always black to dark in color. That does not mean it's mafic. It's obsidian. It's kind of got its own rules. And so obsidian, right? Glassy texture, cooled very, very quickly. There is one other thing that happens. And that is you have two different cooling speeds. So sometimes you'll have a rock cooling under the volcano slowly, making nice big crystals. Then the volcano erupts. And so now the rock is flowing along the ground surface, cooling quickly. So you can see here you have two different cooling speeds, so you have two different textures, right? You have a larger grain texture here with these, these large-ish crystals forming, and then you get a fine grain texture around it, where the rock is flowing over the ground surface. And these rocks are called porphyries. There's a whole thing about figuring out what kind of porphyry it is. We're not going to worry about that. And so here you have two cooling speeds, right? You have an initial slower cooling speed followed by a later faster cooling speed. So igneous rocks tell you thermal history, right? They tell you where the rock cooled. And they can tell you about the chemistry of the mantle of the earth or anywhere in the interior of the earth, because as these rocks come up from the mantle, they maintain that mantle chemistry, and so we learn a lot more about them. We learn a lot about the mantle from the rocks that we have that came up from the mantle. And so what about sedimentary rocks? So remember that sedimentary rocks form from either sediment or chemical precipitation, right? So, for example, sediment, I can take this sand and I can turn it into sandstone, right? So go to the beach, there's sand, turn that into rock, compress it, dewater it, cement it, and you get sandstone, right? Or, like with this limestone we've been looking at, I can precipitate calcium, carbon, and oxygen in seawater and make a rock, right? These are called chemical sedimentary rocks. And there's a few different kinds. For example, this is limestone. 90% of the rock in Florida is limestone. The other 10% is chert, which is silicon and oxygen precipitated out of seawater. And so most of the other rock in Florida is chert, or at least the rock on the surface that's native to Florida. But you can also precipitate just salt out of seawater, right? NaCl salt. This would make rock salt. If you licked it, it would be salty. Don't lick the rock. If it had a crystal structure, it would be halite, right? But it doesn't, right? If this had a crystal structure, it would be quartz. If this had a crystal structure, it would be calcite, right? So all of these chemical sedimentary rocks are just a crystal structure away from being a mineral. But they're not. They don't have a crystal structure. There's also kind of a subdivision of chemical sedimentary rocks called biochemical sedimentary rocks. For example, coal is a biochemical sedimentary rock, right? It is formed directly from plant remains. We talked about this with plate tectonics. Swamps make coals. There's a few other biochemical sedimentary rocks, but coal is the main one. Now, clastic sedimentary rocks are the ones, come on, next slide, there we go, are the ones that are made out of different, made out of other rock, right, or pieces of rock. Now, we classify these according to the size of the grain that makes them up. So, for example, the words pebble, sand, silt, and clay have very definite meanings for geologists. But we can rely on your intuitive idea about what a pebble is, right? You don't know how big a pebble is, right? You've been to the beach, you know how big sand is. Silt is about the size of baking flour. Clay is very, very fine. Okay. But we have something called the Whitworth grain size scale that shows us exactly where these size cutoffs are. We're not going to worry about that, right? We're just going to say, okay, look, pebble, right? Pebble. If the rock is made out of pebble-sized particles, we call that a conglomerate, or a breccia if they're kind of angular, but let's go with conglomerate. All right, so here's one, right? You can see where the pebble popped out here, but you can see pebbles sticking out of the rock. Here's one in the field, pebbles, sticking out of rock. Conglomerates form in rivers, and this is the thing about clastic sedimentary rocks, is they form in different environments. And so if you know the environment of deposition for the rock, you know what environment was there millions of years ago when the rock formed. And conglomerates form in rivers. This is the East Fork of the Cherry River near Richwood, California, Richwood, West Virginia. my family are from there, and it just so happens that there's a coal seam back in here, by the way. But if I walk um, down off of the bridge that I'm standing on here, point my camera straight down, and take a picture, it looks like that. All these rounded pebbles, right? If I cement these together, it makes a conglomerate. Conglomerates form in rivers. They can form in the rivers associated with glaciers or even directly with glaciers, but mostly with the rivers associated with them. But you can see here, this is from the Athabasca Glacier in the Columbia ice fields up in Canada. But you can see all these different rocks laying on the ground here, and if I cement them together, I get something that looks something like that. That's a glacial conglomerate there, and yeah, lots of different kinds of rocks all cemented together. Here's a conglomerate. This is fun. This is a conglomerate on Mars, y'all. We don't call off the rules just because we're on Mars. Conglomerates form in rivers. Conglomerates are associated with water, and so this is one of now several lines of evidence that there used to be water on Mars, and this is how we know is we find the kind of rocks that form in water. What about sand making sandstone? Here's one thing. Okay, sand makes sandstone. Okay, there's a lot of different kinds of sandstone, and it forms in a lot of different kinds of environments. This is a sandstone that used to be a desert, right? Deserts obviously have a lot of sand in them. If I cement that together, it makes a sandstone. Beaches have sand in them. As we know, we've all been to the beach. If I cement this rock together, I make sandstone. And so, once again, cemetery rocks provide us with a valuable way to sort out past environments. For example, I showed you this picture when we talked about plate tectonics and this ocean running up through the center of North America here, called the Sundance Sea, or the North American Epicontinental Interior Seaway. This was about 70 million years ago. Well, how do we know that, right? How do we know that there used to be water running up through here? Well, look at the rocks, right? If I go right about there and I start looking at the rocks, right, they look like this. These are sandstones. These are marine sandstones. They formed in oceans, right? And this particular rock is the Horseshoe Canyon Formation up in Alberta. I took this picture a couple summers ago, but that's how we know this ocean was there, right? When you look at rock that is the appropriate age, it shows the evidence of being covered in salt water. It was an ocean. Okay, and so yeah, but once again, lots of different environments make sandstones, right? Oceans, sometimes rivers, deserts. I mean, there's all kinds of. I mean, think about in your life right now, everywhere you see sand, that could make a sandstone. So if you bring me a conglomerate, I'm going to tell you it formed in a river. You bring me a sandstone, I'm going to ask you where you found it, and we're going to look at it a little bit closer to try to work out a depositional environment for that, though. Another easy one, though, is silt. Making siltstone. Siltstones form in lakes. It's a glacial lake. I have a lot of pictures here from my trip from Canada. This was also up in Canada. That picture hasn't been filtered or photoshopped or anything like that. It's just that color because of the silt. And so the bottom of these North Temperate lakes make a really interesting sediment deposit called a varve. Each light and dark set of beds here is 1 year, and a good archaeologist can tell you what year. Now, this isn't happening at our lakes. This isn't happening like Lake Okeechobee or something like that. You need to be pretty far north, but when it does happen, it's a very, very valuable thing because, like I said, a good archaeologist can tell you what year that was. And so if you pull an artifact, for example, out of that lake, you know how old it was. So it's a very, very valuable thing, like I said, for archaeologists. These silty lake deposits. Now, if archaeologists love their varves, and oh my gosh, they do, y'all. Paleontologists, we love our shales. If I take a very, very fine grained sediment, a clay, and I cement that together, it makes shale, and it frequently preserves fossils. Back to Canada, this is Mount Burgess near the town of Field in British Columbia, home of the Burgess Shale. You hike up there, on top of that thing looks like that. Really pretty, and those shales have some really amazing and crazy fossils in them. Things with arms sticking out of their mouths and spikes and just all kinds of really weird stuff. The Burgess Shale is a remarkable fossil deposit, and you can see a lot of it at our Smithsonian Institution. Just really remarkable. So sedimentary rock tells you environment of deposition, right? Different environments produce different sedimentary rocks. And so if you go somewhere like the Grand Canyon, here's a schematic of it. As the sedimentary rocks change as you go up, that represents environments changing through time, right? When we do geologic time, we'll learn that the older rock is down here, the younger rock is up here, and so as these rocks change, going from a limestone to a shale to a sandstone, that represents a change in environment. It's a very valuable tool for geologists. Finally, we have metamorphic rocks. Metamorphic rocks form from applying heat and pressure to pre-existing rock. I always like to compare the process of metamorphism to cooking, right? Where you take, something that, like bread dough that is not really edible, but I apply pressure or rather heat to it, give it, 20 minutes or so in the oven, and it comes out bread. Right, I can apply pressure too, right? Pressure cookers, Instapots, cook food by applying both heat and pressure to them. Metamorphism, right? Well, that's what we're doing to rocks, only much longer time periods. There's two kinds of metamorphic rock: foliated and non-foliated. Foliated metamorphic rocks have a kind of a layered texture to them. You can see that nice there with that layering in it. That's the foliation. Non-foliated metamorphic rocks don't have that mineral alignment or that texture to them. You can see a piece of marble down there that doesn't have any foliation in it. Marble's not the only non-foliated metamorphic rock. There's a few. Here's a quartzite made from sandstone. So you take a quartz sandstone and you apply heat and pressure to it, you make a quartzite. These can be a little tricky to tell apart. Sandstones, though, tend to have more or less rounded grains, and there tends to be some space in between them. Quartzites, the pressure has pressed the grains together. They've melted wherever they've touched. That's called pressure solution. And they end up interlocking like this. Like I said, you just pick them up, and it can be a little tricky, but you can tell them apart. If I take the biochemical sedimentary rock coal, in particular, let's be a little more specific, bituminous coal, and I apply heat and pressure to it, I make a metamorphic rock called anthracite coal. It's kind of shiny. This is considered to be very high-grade coal. And by that I mean, if you absolutely positively have to burn coal, don't burn coal. Just don't burn coal. But if you have to, this is the good stuff to burn because you get a lot more heat out of it than you put into it. But once again, you really ought not be burning coal. It's nasty stuff. Don't burn it. If I take a conglomerate and I metamorphose it, I make a meta-conglomerate. So I have a sedimentary rock with pebble-sized pieces, and I compress that, it flattens the pebbles. This is handy because it tells you what direction the pressure was coming from, right? It's coming from, this way. This is a very good meta-conglomerate. They're not all this obvious. Sometimes they look like this. So in that case, what you have to look for is the cracks. in a conglomerate, the cracks will run around the pebble, right? And pebbles will pop out of them and stuff like that. In a metaconglomerate, the pressure has kind of fused everything together, and now the cracks will run across the pebbles. And I can't really find one there to show you. I don't see one there. Oh, maybe right there, maybe. So, but that's just kind of one of those silly geologist tricks that we can use to tell a conglomerate from a metaconglomerate. Is look for the cracks if the pebbles aren't just flat like that. Okay, so these are non-foliated metamorphic rocks, right? So what about foliated metamorphic rocks? These rocks with layering in them. Well, there's a few different ones, and the nice thing about foliated metamorphic rocks is that they can tell you how much heat and pressure there was. They can also tell you the direction of the heat and pressure. The direction of the heat and pressure is always perpendicular to the foliation. And so if you only apply a little bit of heat and pressure, you get a rock called slate. And here's a piece of it. Here's what it looks like out in the wild. It breaks very, very flat. And so makes a really good ornamental tile. You see it a lot as flooring tiles and things like that. It can also make pretty good roofing material. Not so much in Florida just because it's so expensive to haul it here, but in places where you have a lot of it, you see it a lot as building material and roofing material and stuff like that. If I apply a wee bit more heat and pressure, I make a metamorphic rock called a phyllite. The surface is kind of shiny. It's starting to wrinkle up a little bit. It'll still break, but not that flat. But it will still break pretty flat. And then if I apply even more heat and pressure, I make a rock called a schist. Now you're getting a lot of what we call secondary minerals. You find a lot of garnets in schists. You find a lot of mica. The mineral mica, it's just mineral that tends to break very, very flat in these very, very thin sheets. You find that in schist. You find tourmalines. You find all kinds of interesting secondary minerals hanging about in these schists. The bottom of the Grand Canyon is a schist. The Vishnu schist, and here it is right here. This is all schist with some, with I believe a sandstone sitting there on top of it. And then if I apply even more heat and pressure to the rock, I make a rock called gneiss. Gneiss rock, I know, everyone always makes that joke. These very distinctive dark and light bands running across it. This is a very, very high-grade metamorphic rock. We find a lot of this today in the Appalachian Mountains. When you go today and you look at the Appalachian Mountains, you go into the Appalachian Mountains, you are seeing the ground down nubs of a formerly much taller mountain range. You really are. And the reason we know that is because the rocks that we find on the surface of the Appalachians are normally the rocks that are very, very deep in the Appalachians, or deep in mountain ranges, like gneisses and high grade schists. Gneisses go well with granites because a lot of times the gneiss will form from the granite. Or if I heat this just a little bit too much, it'll melt. And if it melts, because this is the thing about metamorphism, right? You apply heat and pressure, but not so much heat that you melt it. If you melt the rock, you just made magma. And that's going to cool, make an igneous rock, right? And so metamorphism is really tricky because it happens in high pressure, high temperature, long-term solid state chemistry. It's really fascinating stuff. This is not the chemistry that you do in a normal chemistry lab. Here's a picture of a granite and a gneiss sitting right next to each other. There's a gneiss there. There's a granite there. And what happened here is we had enough heat rather, to melt the rock. Only this didn't melt. This did melt because it was wet. Probably had a little bit more water in it, and that lowered the melting temperature just enough that this pocket right here turned into magma and therefore recooled into granite or something like it, while all around it the rock metamorphosed and turned into gneiss. And so a lot of times we have like granitic gneisses or gneissic granites. They really do go together. So anyway, alrighty, there is rocks and a wee bit of minerals in a nutshell. You have You have a lab exercise where you learn a little bit more about how to identify these. So, but you should be ready to go on that now. So everyone take care, and I'll talk with you later on. Bye-bye.